So this is the general algorithm for in order for you to develop an artificial neural network. Yes, you can see the first step, of course, during the training process. This is the first thing you need to do, where you need to initialize the wake with adequate value. Here, when I said wake, does not mean only the wake. Means that it's not just a wake. You also initialize your B. Means that initialize your W and your B. So in general, there's a two way to initialize this value. There's a two way. One is you can generalize by set all W and B equal to 0, or in some application they just put a random number, means that set W and B into some random number. Okay, you can set into any random number, because in programming you have a random function that can generate a random number. Then you can set your W and your B with a random number. There's a advantage and disadvantage of using there's a effect of using, there's a some effect, different effect of using either you initialize your W and B with 0 and initialize your W and B with random number. But I don't want to discuss that, because that is some which is not covered in your syllabus, but you just realize that I just hope that you can remember that some people use initialization with 0, some people use the initialization of W and B with a random number. Later when I show you some example code in MATLAB, I'm using a random number to set my W and B. Okay, first you need to do that. Once you know, or once you set your random number, once you get the random number and you set your W and B, for example, then means that you already know the initial value of your W and B. And then after that, enter the input from the training data WXY and obtain the neural network outputs. Means that this is actually a forward pass. Okay. Okay, means that you take one sample, you pass into your network, and then once you find your network, once you calculate all the input function and all the activation function, at the end you will get your predicted Y, which is Y hit. And then after that you will do some comparison between this Y and this Y, where actually you will get the error there. Okay, once you know the error, so that is step number 3. Calculate the local error of the output neuron and delta. So this is how you calculate. Again, this one and this one come from this step. Once you know this one, then you might get your local error there. So this actually represent the local error belongs to your output layer. Once you get the local error belong to output layer, so again I use a bold there, bold fonts there, meaning that this is vector. Once you find this one, then you need to do the Hadramard product or piecewise multiplication between your E and your F apostrophe to get your delta M. So meaning that this delta M means, okay, sorry to interrupt a bit. I forget to define what is M. M is actually, you must set here, set number of layer. If your if the number of layer equal to 3, it means that your M equal to 3. Like our example, our previous simple example, the M is equal to 3, means that you will have 3 layer. Layer number 1 is input layer, layer number 2 is hidden layer, and layer number 3 is output layer. So now M equal to 3, this one equal to 3, this one equal to 3, this is one equal to 3, and this one equal to 3. So means that this is how you compute the delta at the output layer. Then step number 4, you propagate the output neuron delta. You propagate the output neuron delta, which is delta, backward, and calculate the delta of hidden layer. Means that you propagate this neuron to the hidden layer to calculate the delta at the hidden layer, which is I represent in this one. So I'm using the for loop here, means that in our example here we set our m equal to 3. So now this one should be equal to 2. Okay, is equal to 2. So for k equal to 2, 2 means that this for loop only do one iteration only, one cycle only, because for k equal to 2 means that you are only apply, there's no there's only single cycles there to execute this one. So then you compute this one, where actually to find now this one is actually your hidden layer, your layer k equal to 2, because your k now equal to 2. Okay, this one is 2. So your E2 is equal to your W2 piecewise multiplication with your delta 3. Okay, so once you get this E, then your delta 2 equal to f apostrophe net 2. Oh, sorry, this is dot. Okay, sorry, this is dot. Okay, this is dot, and this is the piecewise I'm sorry, element wise multiplications between your apostrophe f and your net 2 there. So because this one is not looping, it just execute one cycle only, then finish. Then you get the delta of hidden layer. Once you get the delta of your hidden layer, and then step number 5, then you can adjust the weight according to the following learning rules. Of course, this is gradient descent. Once you know your W for each and every layer, you have your delta 3 here, you have the delta 2 here, then you can compute the updater of this one, then you update this one. Okay, I'm sorry, this one should be yeah, this one should be minus. Okay, because the some textbook using plus, I'm using minus there. Okay, maybe if you find out some textbook using plus there, that's actually because they at the derivation they already take out the negative value, and that negative value will neutralize this operation. That's why this operation become plus, because I'm not take out the negative value, I still put the negative value at the derivation. So that's why the original operation should be minus there. And then repeat the step 2 to step 5, means that you must repeat step 2 to step 5 at the other sample. I mean, this is only this one cycles there. Okay, it's just a one samples. It's a one sample process. Once you update the W, and then you must repeat the step number 2 again to step number 5 using another sample function. Means that assume that you have 100 data set, so then you need to repeat step 2 to step 5 100 times, and then each and every sample you will update your W. Okay, so and then of course once you finish all the compute the 100 data set, okay, that is called as okay, again assume that your data set is the number of sample inside your data set is 100, meaning that you will have a collection of x1, y1, x2, y2. So you go, your data set have this is what I meaning is that is the training data, is a training data. So the last sample should be x100, y100. So and you must repeat step 2 to step 5 for each and every sample here means that this is the first one, execute step 2 to step 5, and then you again repeat the same things, step 2 and step 5 for these samples, and then you repeat again up until 100 data. Okay, once you complete this 100 data, so this is called as, okay, once you complete one cycle, means that one cycle in processing the whole data set, in this case is 100, means that you repeat 100 times. So this is called as one epoch. Okay, please try to seriously take note of this one, because I don't have a slide describing what is epoch. Okay, so this is where I want, because this is you must take note of this one, because I don't have a slide explain this one, this fact. This is called as one epoch. What is the meaning of one epoch? Is that one epoch is similar to when you do the training, you already complete the whole data set. In this case, because your data set is 100, then you need to repeat step 3 to step 5 100 times. Once you finish that 100 times, is called one epoch. But since to complete this one epoch, you need to repeat step 3 to step 5 100 times. Okay, 100 times repetition. This repetition is called iteration. Okay, so means that in this algorithm, one epoch is equal to 100 iteration. Okay, so means that if you go apply here and then you repeat step 2 to step 5, each and every step you update, each iteration you update the W, then that is actually you have update 100 times, because you are repeating from step 2 to step 5. And then once you finish that one, and then you can see that at step 7, repeat step 2 to step 6 until the network is properly trained. Means that here, every time you repeat one time this step is actually is equal to one epoch. Okay, because repeat step 2 to step 6 means that once you complete step 2 to 5, and then one time you complete step 6 means that you already repeat this 100 times. So means that step 7 here, once you complete one instruction at this site, is actually one epoch. So that's why in order to converge, to find a converge, to converge your neural network, or to find the optimum neural network, normally you will set as this one. For example, you can set epoch equal to 1000. Means that doesn't matter what happened at this element, you must repeat 1000 epoch. Once you finish 1000 epoch, that is the optimum value that you can get. Okay, so meanings that just imagine that this is your E. Remember that the cost function, that E. Okay, the cost function. So assume that our functions have a converge functions there. So means that this is the minimums. This is the one that we want to find, which is to find the W and B that can represent the minimum value over there. When we apply the initialization, we just select a random number. Let's say once you set with the random number, during the feed forward, this is where you start, for example, and then you update your W is going toward this one, it is going toward that side, and then you, for example, let's say that step belong to, I'm sorry, okay, let's assume this is actually represent one epoch, means that after you update your W or the B 100 times, one epoch, and then this is second epoch. Okay, sorry, okay, that is second epoch, and then third epoch, and then you will repeat it fourth epoch, and then you will do it at the 1000 time. So of course the basic algorithm for artificial neural network, you don't have any stop criteria. There's no stopping criteria, so you just repeat, you just execute up until 1000 epoch. Of course the more advanced ANN algorithm, they also introduce with the stopping criteria, but for you to understand the basic concept for ANN, I don't introduce to with the stopping criteria, but you can see that doesn't matter if you do, let's say if you don't have any stopping criteria at all, it will repeat up until 1000, it will stop. But what happened actually, let's say if you talk about the stepping process there, it will repeat up until 1000, but at the end you will find out, let's say at the epoch number 100, okay, you already arrive at the valley here. Then what happened at the 101, it might be a little bit going into this side, okay, let me draw a little bit, okay, that is the point at the 100 there. So 101 should be going into that side, and then 101, 102 going into this side, so 104 going into the side. So if you repeat 1000 times, meaning that your points there will play around at this valley, means that you will repeat up until 1000. Once you finish at the 1000, it can be here, it can be here, or it can be here, which is close to this point. Okay, if you, let's say you set the alpha bigger, meaning that at the your jumping process is very big, means that you can go up until this one, first epoch, second epoch, third epoch, and then you repeat at the up until 1000, it might be something like this, and then at the end it will go into this 1000 up until 1000. So meaning that that's why you need to set a proper alpha. Once you don't, if you set too big, then you will if you repeat at the 1000 epoch, it will play around like this up until 1000. Let's say you finish up until 1000 at that one, then that is the optimized, but actually the real optimized is not that one. It's you can go deep there. So that's why you need to change the alpha into smaller alpha. Of course the trade-off there, the stepping process is a little bit slow, the training process or learning process a little bit slow, but you can find a more best optimized point than you set a big alpha. But of course why we set the epoch bigger here, at the end doesn't matter you arrive here at epoch number 100 or at epoch number 200, for example. At the end, if you set the epoch bigger, then it will stop there, means that it's just change very small changes there up until they finish 1000 times there. Once they finish 1000 times, that is where you get the optimum versions. Okay, that is the basic ANN model where we don't apply the stopping criteria, but the more modern ANN algorithm and deep learning algorithm, they already apply the stopping criteria, where actually they will stop before they arrive at the epoch equal to 1000. So that's how in general how it works. Okay, the other things I will like to highlight in this slide is that, if you realize that, okay, you can see that when I explain this example, I set my m equal to 3, which is similar to the one that the example that I giving you before, which is the first layer is input layer, and then you have hidden layer, then you have the output layer. So that's why 1, 2, 3. So you can see that this algorithm is already generalized, means that doesn't matter actually how many layer, you can still using the same algorithm, the same code there. Let's say I set this one, I want to add more hidden layer, I set my m equal to 4. What will happen? Okay, you will have 4 layer there. This one is input layer, this one is hidden layer number 1, this is hidden layer number 2, this is your output layer. So you still can use the same step here, meaning that still m here is now equal to 4, means this e here is e4. So again, this is your e4 at this part. So it's belong to the local error which is happen at the output layer. And then this is also the definition of delta 4, where delta 4 you must multiply the f apostrophe with your e at the output layer. So you can see that here, why I separate between this operation and this operation, you can see that because of the definition of e is different. This one, okay, this one is to find the e for your output layer, but this one is to find the e of your hidden layer. So doesn't matter if you add another hidden layer here, the definition is still similar. Means that if you want to find e at this layer, then it's depend on your w doesn't matter, the w that going into this delta and another w going to that delta. Let's say this is 1 neuron, this is 1 neuron. To find e over here, again this e is also the multiplication of your w and your delta of your hidden layer, the second hidden layer. Let's say you have a delta here, and then let's say this, you don't have only two neuron, you have 3 neuron. This is also delta. So to find this e, then you need to multiply this w with delta, this delta plus this w multiplied with this delta plus this w multiplied with this delta to find this e. Okay, so that's why the expression here is still similar. So that's what I means that what I meaning is that doesn't matter if you add more and more hidden layer, this equation is still similar. Okay, you can see that now for m equal to 4, this one will become from 3 to 2. Okay, I forgot to mention that this is this step is actually is not increment, it's a decrement process. It's a decrement from 3 to 2. So means that it's actually 3. How to write that one? I think in MATLAB use something like this. If you you must write something like 4 k equal to 3 dot minus 1 dot 2. So it's a increment, it's a decrement looping index, it's a decrement index looping, meaning that you will process because this behavior, this operation is a backpropagation, means that you must calculate this layer first. Once you get this one, you get layer number 3, and then you get the layer number 2, and so on. So meaning that is going into that direction. So so if you are using the layer number as an index and this for loop, then you need to do the decrement index, it's not increment index. So you can see that now this looping process is repeated 2 times. The first time you execute this line, you want to find this delta. The second loop, you execute this operation, you want to execute the delta at the hidden layer number 1, or in this one is called as a second layer. Okay, this is first layer, second layer, third layer, fourth layer. So hidden layer number 1 is actually a second layer. So that's why you need to have a for loop here. Means that doesn't matter if you change the m into 2, 5, 6, 7 and so on. Actually you are increasing more and more numbers of hidden layer, and this is where actually this will repeat one line by line, because the function to execute E and delta at the hidden layer is similar. Okay, the one that is different is just output layer. The output layer, this is the definition to find the E. It's not similar with the hidden layer, but hidden layer doesn't matter, you added more and more hidden layer, you still using this expression to find the E. So once you find the E delta, and this delta you already compute, this delta you compute, then you can find all the updater belong to this neuron, an artificial neural network, and then you can update. So you can see that doesn't matter whether you increase the number of neuron in each layer or you increase the number of hidden layer, you still can't repeat, or you still can use this general step in develops the artificial neural network. So doesn't matter, let's say if I want you to design something like this, for example you have a 3 output, and then here you have 4 output at this side and 1 output at this side. So by using this step you still can develop this model. Okay, so that's why the purpose we have go along in derive a simple architecture, and then we do a lot of derivative there, all the derivations there at the end, and the final step where we manage to find the general step that can represent any architecture you want to design. You still can repeat the same process, or you can still use the same algorithm as you see in this slide. Okay, so that's why I introduced to you with delta and E. That is the purpose, because we want to generalize everything's there. Okay, so regarding the learning rates, I don't have to explain, you already know that. Okay, it's the step size, and if you put a small value, then the step size is a little bit slow. So that's why when the learning rate is very small, then the learning process is very slow. When the learning rate is the value is big, then the learning process is very fast. But the trade-off there, or disadvantage of setting the learning rates higher, biggest, then you cannot find the most deepest point at the values there. So, okay, it's just play around with some big step there. Okay, so this picture just show you what happened actually during the backpropagation. You give the input, a single input, and then once you predict the, okay, you can see that this is your X there, a sample training data X1, X, and then from there you go in this direction, is a forward pass, and then you find the Y head there, and then you compare your Y head with your, of course this is Y, your Y. So let's say this is first sample, right, the first sample, and then this is the predicted output from the first sample. You can compare with this one. Okay, this is your Y1. So this is where you find your E1. So once you find your your E, the local error, from your errors there, you will update your network. Means that you want to find from E, you get all the delta. From the delta, you will get the gradient. Okay, the gradient of your W, and then from the gradient of your W, you can get the updater of your W. So not just W, it can be, okay, it's not W only, you means that it's W as well as your B. Okay, so From this gradient you get your updater of your W and your B. From there actually you will update your wake and your bias. Okay, update wake update as well as bias. Sorry. Okay, as well bias update. So this figure just show you summarize everything what happened, and then that is for single input, single from the single sample you update the W. Okay.